Good morning to everyone on the West Coast, good afternoon to everyone on the East Coast, and good evening to everyone joining us from Europe. Welcome to the NEO Technology Graph Database webinar series. I'm your host, Adam Frankel. Today, we'll be talking about the introduction to graph databases with Emil Eifrem. Emil is the CEO and co-founder of NEO Technology and co-founder of the Neo4j project. Before founding NEO, he was the CTO of WindAB, where he headed the development of a highly complex information architecture for enterprise content management systems and saw the need for a graph database. Before we get started today, I'd like to make some brief introductory notes about the webinar software we're using. On the right-hand side of the screen, there is a question and answer box. Please feel free to type in questions at any time. We will have time for questions set aside during this webinar. However, I already know that we won't be able to get to all of the questions asked today. If we don't get to answer your question, please feel free to go to the forums page on the neo4j.org website and ask your questions there. Also, I already know what the most commonly asked question is going to be. Are you making a recording of today's webinar? And the answer is yes, we are. And as soon as we upload the recording to YouTube, we will send a link to the video out to everyone who attends this webinar today. Okay, without any more introduction, I'd like to turn the webinar over to Emil. Emil, please take it away.
Thank you, Adam, and welcome to everyone. So today we're going to talk a little bit about graph databases. We're going to do a brief introduction, talk about the high-level concepts, and we're even going to dig into some actual code. Before that, though, we're going to zoom out a little bit and talk about where graph databases fit in the world of NoSQL and what kind of applications are very good sweet spots for graph databases. This webinar is fairly interactive. We're going to run a couple of polls so that you can participate during the course of this webinar. But as always, when I give my presentations or webinars, I welcome feedback on all channels. In the bottom right-hand corner of the screen, you see my email address as well as my Twitter handle. And feel free to tweet during this webinar. The only thing that I do ask of you is to use the Neo4j hashtag that you can see there. We monitor the Neo4j hashtag religiously, so if at any point in time you want to reach out to us, that's a good way to start. Okay, so what's the plan? Like I mentioned, we're going to start by zooming out a little bit and talk about NoSQL, the broader landscape of alternative databases, and where graph databases fit, in that. Then we're going to dig into graph databases specifically. We're going to talk about some code and show some examples and talk about the basics. We're going to look at some use cases that are emerging as sweet spots for graph databases, and then we're going to wrap up and hopefully have time for some questions. Without further ado, let's dig into NoSQL. But actually before that, we're going to run our first poll. Adam, can you run it, please?
Certainly. Okay, so the first question we want to know is, what is your level of graph database familiarity? And we've set up this poll so you can select multiple answers, and you can select all that apply. So option 1, I had never heard about graph databases before this webinar, or I have been casually following Neo4j or other graph databases, or I have played around with Neo4j for evaluation purposes, or I have built or am building a real project on Neo4j. And the last option is, I have put Neo4j into production. And I've got to tell you, I'm honestly questioning, if you click that last one, then why are you attending today's webinar? But I'll let you make your choices. Please make your selection in the next few seconds so I can close this poll and show the results. Okay, let me do that and share the results with everyone. Okay. So 50%, I have been casually following Neo4j or other graph databases. 34%, I have played around with Neo4j for evaluation purposes. 28%, I had never heard about graph databases before this webinar. And 16%, I have built or am building a real project on Neo4j. No one has selected, I have put Neo4j into production. Thank you very much for participating in this poll.
All right, that's great. We have, sounds like 50% have casually been following Neo4j or other graph databases, and some have actually started even hacking some code with Neo4j, which is perfect. So before we dig into Neo4j and graph databases, let's talk a little bit about NoSQL. So NoSQL is one of the big memes of this year and actually even of last year. It's one of the acronyms that took the tech world by storm, and it has a little problem. It's a good indication of a huge transformation that is going on in the database landscape, but it's of course a horrible name. Everyone hates the name. A lot of people think that NoSQL means never SQL, never SQL. People think that NoSQL is no to SQL or no to SQL, but nothing could actually be further from the truth. The truth of the matter is that NoSQL is simply not only SQL, as in the observation that in the backends of today and very much in the backends of the future, we're going to have not only SQL, but also key value stores and document databases and graph databases. So the observation here is not that we're going to throw out SQL, but rather that the world of the one-size-fits-all database is gone. We're now in a world where information is so big, so huge, and so complex that the job of the information architect of the future will be to take that big data set that pretty much everyone is going to have, and you're going to identify parts of the data set that fits well into a relational database, and you're going to put it in that. Other parts of the database of the data set may be very key value oriented, and that should best belong in a key value store. And other parts of the data set might be very graph oriented, and that's where the graph databases come in. So it's not a counter movement to SQL, but rather a complementary movement. So one of the problems with being associated with the hype is that a lot of people, a lot of projects want to attach yourself to that hype. So it seems like there's a new NoSQL project launched every week now. But if you squint a little bit, you can see that there's 4 broad categories of NoSQL. The first category is that of the key value stores. And the key value stores were all inspired by a paper, a research article actually, published by Amazon a couple of years ago called the Dynamo paper. And Dynamo outlines a storage architecture for Amazon that they use to get to the super high volumes of e-commerce transactions that Amazon are subject to. And they basically said that, hey guys, we tried to build this using a relational database, sort of the standard architecture that everyone has been using for 20, 30 years. And we failed because the relational database was not the best tool for all the jobs that we had internally. So we sat down and we reevaluated, and we built this key value database that we call Dynamo. And the data model here is basically a global collection of key value pairs. You can think of this as, if you're a Java programmer, java.util.map, but globally available. If you're a Python programmer, it's a Python dict. And there's equivalents in all languages. So basically a hash table that is globally available and contains key and value pairs. There's a bunch of open source implementations. One of the most popular ones is called React. There's also Project Voldemort out of LinkedIn, and Tokyo Cabinet and Tokyo Tyrant out of Japan. So that's the first category of NoSQL. The second category is called column family or big table. And in the same manner that the key value stores are inspired by Amazon's Dynamo paper, the big table clones or column family stores are inspired by Google's big table paper. And Google basically said the same thing. Hey guys, we've also been able to push our systems to some scale. And we also did it by throwing away the relational database, not for all tasks, but for some tasks. And the model we've chosen is that of a big table. So it still has a tabular model, but not a relational model. And so the core difference here is that whereas in a relational database, every row has to adhere to the schema of the table to which it belongs. In big table, every row can have an individual schema. So you can imagine having one row, if you build, for example, a salary list, a payroll system, you might have columns called name, first name, last name, salary, title, right? And which works fine if you have only one title. But then there may be people who move around in the organization, wear multiple hats, and they might have 3 or 4 titles. And the challenge in a relational model is how do you fit that in there? You can add 3 or 4 columns to your relational table, title 1, title 2, title 3, title 4. The problem, of course, is that that ends up punishing all the rows that do not have just one title. I'm sorry, all the rows that do not have 4 titles in this example. And the big table model can handle that. So then you can say that, oh, just this one row has actually 4 titles. And that's going to be very flexible and won't end up punishing the other rows. So that's the big table data model. Examples in here at HBase, which is part of the Apache Hadoop project, very popular. Hypertable, the C++ implementation, and Cassandra. The third model is called document databases, and this is probably the most popular NoSQL data model today. It's the most popular implementation here is called MongoDB. Another very popular one is called CouchDB or Couchbase. This one is not inspired by a research paper, but rather by a specific system, and that system is called Lotus Notes, which is some of you may know as an email system, and probably not the most sophisticated email system by today's standards, but it actually has a really cool backend architecture. And that backend architecture uses abstractions called documents. And documents are key value collections, and you can have multiple of these, multiple collections, multiple documents in a document database. And then the fourth category, and where we will spend most of our time today, is called graph databases. And sort of tongue-in-cheek, inspired by Euler, who, if you recall your computer science or your mathematics, was an old mathematician in, I believe, Switzerland, who invented graph theory. And the data model here is that of nodes, key value properties that you attach to both the nodes, and then typed relationships between nodes that can also hold these key value properties. Examples here are Infinite Graph, Sonus, OrientDB, and now, of course, Neo4j, which is the project that I'm most familiar with. You can look at these various NoSQL data models along 2 axes. A lot of people talk about scalability as being the core driver of NoSQL, and that is a very important one because dataset size is growing exponentially every year. But a lot of the analysts and thinkers around NoSQL are now coming around to the fact that dataset size is a really important aspect, but it's not everything. And actually it turns out that the most important driver of NoSQL systems today is data complexity. And dataset size on this axis, the y-axis on this chart, is basically how does your system cope with more and more data that looks sort of the same. Whereas data complexity is how does your system cope with more and more data that does not look like the other data in the system. More and more connected data, more and more semi-structured data. And if you look at these 4 models, we have the key value stores all the way to the left. They have a super simple data model, just key and value pairs, that's it. Which makes it really difficult, really challenging for you as a programmer to store complex data. But the upside of this is that because the model is so simple and because it completely eliminates connectedness from your model, from your data, you cannot store connected data in a key value store. Because it prohibits you from storing connected data, it's really easy to get it to scale out in size. And scaling out in data set size is all about horizontal scalability, i.e. the ability to add more and more database instances and thereby scale horizontally as you have more and more machines. So the key value stores are great at storing big data sets, but very challenging to put complex data in there. Then we have the column family or big table guys that are slightly more challenged to store data set size, but better at complexity because they have a richer data model. You have the document databases, and all the way to the right are graph databases. And of course, the reason that I am most fascinated by graph databases is that if you look at the average systems out there, if we take away the 4 or 5 big outliers like Google and Facebook and Yahoo and some of the biggest web properties in the world, if we take away those, the challenges that face everyday programmers out there is not that of how can I get my system to scale from 1,000 machines to 1,100 machines. I mean, most programmers just don't face that in their everyday job. The challenge rather is how can I represent my complex data set in the database. So I'd say that at least 90% of the use cases out there live substantially below the scalability, scaling to data set size characteristics of these NoSQL systems. This is us, graph databases, and let's zoom in on that part. But before we do that, Adam, can you run the second poll?
Certainly. Okay, so now we have a new question for everyone here. Why are you interested in graph databases? And we've also set this one up so that you can make multiple selections. Please select all that apply. Right? So the first option is, I'm not actually interested, I clicked the wrong link. The second option, many domains are graph-oriented, and that maps poorly to tables. The third option, performance problems with SQL joins due to connected data. And the fourth option is graph databases will become important to my profession. So please make your selection in the next few seconds so that I can close this poll and share the results. Okay. I thank everyone who's given me a result. Okay, thank goodness. No one selected, I'm not interested, I clicked the wrong link. 68% say many domains are graph-oriented and that maps poorly to tables. And then we have a tie at 59%, performance problems with SQL joins due to connected data, and graph databases will become important to my profession. Okay, thank you very much for participating in this poll.
Okay, thank you, Adam. So now that we've talked about NoSQL in general, let's zoom in on graph databases and Neo4j specifically. So we already sort of covered this, but let's spend some more time on this in detail. So there are three core abstractions of a graph database. In the relational model, you have tables and rows and columns. In the graph database, you have nodes. All nodes have an ID, but that's the only mandatory attribute. You have typed relationships between these nodes, and then you have key value pairs that you can attach to both nodes and to relationships. So let's say that we wanted to model a domain out there, and for sake of example, let's use the Matrix, the social network from the Matrix movie. It should come as zero surprise to you that I'm a fan of the Matrix movies, since I even named the company Neo Technology to start with. So the first thing that you do when you map a domain, when you represent the domain in a graph database, is that you identify the entities in the domain. In a social network, the entities are typically people, persons, but they can also be other objects that you want to represent. And these entities are represented by nodes. So in this case, we have a person called Thomas Anderson, and he's 29 years old. Thomas Anderson then is represented by node number 1 here. And 1, by the way, is an anagram of Neo, but that's neither here nor there. The name attribute, Thomas Anderson, is stored as a key value property, and the age as well. And you can see here that Neo4j, the 4J is for JVM because it's built on the JVM, the Java Virtual Machine infrastructure. And so the values that can be stored in the properties are any values that are a primitive in the JVM. So ints and bytes and floats and doubles and booleans, as well as arrays of those and strings. Those are the values that are valid. We are not an object database. You can't take, for example, a socket or a calendar or something like that and store it in there. Instead, you have to figure out how to represent that socket or that calendar as nodes and relationships and properties. Okay, so that's the first step. Identify the entities, represent them by nodes. So other entities that we've identified in our domain here is Morpheus and Trinity. And we attach their attributes as properties. After that, you want to identify how are these entities related to one another. And in this case, Thomas Anderson knows Morpheus and Morpheus knows Trinity, etc. And for this, we use typed relationships. So the relationships, if you recall, are first-class citizen on the same level as the node, so they can also hold properties. And when you work with it on a code level, which we'll see later, you actually get first-class objects out there of the relationships. And they implement the same property container interface. You can go set property on the relationship as well. In this case, we use that to represent the fact that Thomas Anderson has known Trinity for 3 days. That's a very powerful concept, the fact that you can annotate the relationships, how people are connected, how things are connected with actual data. You keep building out the social network. You add more entities, and after a while you get to the bad guy in the Matrix movies called Agent Smith, if you recall. And I'm not sure if you all remember the mythology of the Matrix movies, but you should. If not, you should rewatch the movie again. But if you don't remember the movie, basically the bad guy Agent Smith was actually a software agent. It was a program. And the most evil thing that I could come up with was that he's coded in C++, as you can see here. We keep growing our domain by adding the architect, this mythological creature that ended up creating the Matrix, who's of course has ID 42. And again, in the movie, Agent Smith was coded by the architect. They weren't friends. There was no nose relationship between them, but a coded by. So you can see that here we use a new type of relationship to express how things are connected. One more thing to add is that the IDs that you can see here, 1, 7, 2, 3, 13, 42, attached to the nodes, are all mandatory. When you create the node, you get an ID assigned to that node. And you can't remove it, you can't change it. But that is the only attribute that is mandatory. Everything else you attach as properties. And you can see here how you can express so-called semi-structured information. Morpheus has 3 properties, Thomas Anderson has 2 properties, and Trinity has 1 property. And that's all flexibly stored. And there's no one schema that forces all nodes to look the same. So that's a conceptual picture. What about code? So if we dig into this, I chose to use Java as a language to show the code here. Neo4j has bindings to a gazillion other languages, Python, Ruby, Scala, Clojure, C#, and whatnot. But Java is a language that is readable by most people. So that's what we use for our presentations. So we get a graph database service back from some probably a dependency injection container or something like this. And we use that to create a node. We get the node, we call it Mr. Anderson. And then we use a simple hash map-like interface, set property, get property, to pass in the actual property attributes. When we have created these 2 nodes, we use a factory method on the node called create relationship, where we pass in, create relationship 2, where we pass in, we start with the first node and then we pass in the second node. And then we express what type of relationship that we want to do. In this case, we're going to create a directed relationship starting from Mr. Anderson and going to Morpheus. So it's a directed relationship. In Neo4j, all relationships are directed, but every operation that gets relationships out of the graph, such as the traverser framework we're going to spend some time on later, as well as node.get relationships, in all those operations, you can pass in a direction where you say ignore directionality. You say direction.both. Get all the relationships that are either incoming or outgoing from me. And in that way, you're going to just ignore direction in case you want to express a symmetric relationship, for example, friends. So one of the things that sets us apart in the Neo4j land from many of our brothers and sisters in the NoSQL land is this next slide here. All the mutating operations that you do on the graph has to be wrapped in a transaction. It's very popular in NoSQL land to be eventually consistent, which means that you basically don't support any transactions. And I think that is a very noble method to get to a very noble goal, which is large data set size scalability, scaling out to hundreds of machines. And Neo4j actually supports eventually consistent systems as well. But for most people out there, for the majority of users, you don't have the kind of scale that is required that is needed in order to force people to use eventual consistency. And if you're not there, then what you actually want as a programmer is a core transactional API so that you know that all of these operations will complete or none of them will complete. And when you commit, data is there, guaranteed, durable on disk. If you lose power, a millisecond after tx.commit has returned, your data is there. It will never get lost. So that's a very important distinction in Neo4j versus many other NoSQL systems. So we passed in a type of relationship in here, and the question is, how did we define that? And it's very simple. In our API, this is not something that you as an end user will write, but there's an interface called relationship type, and it just declares a simple method called name, which returns a string representation of your name, of the relationship type name. Anything that implements this interface is a relationship type. So, for example, if you wanted to be completely dynamic and not define your relationship types on demand, not define them upfront, you can roll your own completely dynamic relationship type. And actually, as of recently, we shipped with a relationship type implementation called dynamic relationship type, which is very similar to this class, this simple 3-line class that I've outlined here. But basically, as you can see here, it's a very simple implementation. You pass in the name in the constructor, and that's it. And the way Neo4j works is that if you have two nodes and you create a relationship between them, and you've created this my dynamic relationship type class with a completely new name that Neo4j has never seen before, it's just going to look at this and create it underlying in the store. There's no need to do any create table or alter table. There's no need to shut down the system. It will completely ad hoc dynamically add this new type of relationship, which is very, very powerful. If you live in a very dynamic system and that models a very dynamic world, for example, you might imagine spidering the web and figuring out ad hoc that, hey, these two websites are related in XYZ way. Then maybe you hadn't, when you designed the system, declared a relationship type called XYZ. But as you detect that, you can just create the relationship type, and it's all going to work completely dynamically. Very, very powerful. However, again, most people out there don't have that situation. They actually, when they sit down and they map, apologize, second here. Actually, I had a little bug there where my Skype kicked in. So when most people sit down and design their application up front, they actually draw this on a whiteboard. They sit down and they know all the ways entities can be related. If you live in that world, you can define your relationship types as an enum. So you just create an enum in Java, it implements relationship type, and then you can stack all your relationship types in there. In this case, knows and works for. And if you do that, you get all the benefits of having a static compile time. You have refactoring-friendly IDE. Your compiler will warn you before you try to add a relationship type that doesn't exist or use a relationship that doesn't exist, etc. Another thing that's very interesting, we mentioned whiteboards just recently, is this concept that we call whiteboard friendliness. And this is a very powerful concept inherent in the graph database model. And it is the observation that we did when we were building a lot of systems as consultants on top of graph databases 5, 6, 7, 10 years ago, where we observed the fact that when we took the original snapshots of these original brainstorming sessions that we typically did with our domain experts early on in the project, you got into this room, you brainstorm with your domain expert who knows everything about pensions or retail or banking, but doesn't know anything about computer science or databases. You take, you brainstorm that on the whiteboard. You take snapshots of those, and when you go down and you sit down and you build that system, we observed that 6 months down the line, we could look at those snapshots from the original brainstorming sessions, and we could see a one-to-one mapping from the whiteboard down to the actual data in the graph. And we call this whiteboard friendliness. And I think that's one of the reasons why programming with a graph database feels so powerful and is so efficient, is that you have a one-to-one mapping from the domain model, the way the domain expert thinks about it, and the graph. And I think the cognitive model of the programmer is that of the whiteboard. We may have been trained as computer scientists to take the whiteboard and serialize that, decompose it into tables using ER modeling and first normal form and third normal form and all of that stuff. But I think the intuitive cognitive model is actually that of the whiteboard. And the fact that it's one-to-one represented in the graph is very, very powerful. Okay, so we've now worked on putting data into the graph. The question then is, how do you get data out of there? And for that, there are several ways you can do that. We're going to start by talking about the traversal framework. So if we go back to our example here, and we say that we have the social network from the matrix, and we want to find out who are the friends of Thomas Anderson. Conceptually, what we want to do here is we want to start a traversal, an iteration really, from the first node, from node number 1. And we want to go along all relationships of the node type. We want to go breadth first rather than depth first, because we want all of the friends that are close friends to Thomas Anderson before the not so close friends. And we just want to keep traversing until we get to the end of the graph, until we can find no more nodes relationships. And that way we're going to find all of Thomas Anderson's friends and friends of friends recursively. So the code for that is pretty straightforward, but it is the peak of complexity for this presentation. So if there's one time you should pay attention, this is it. So what we want to do here is we want to use the traverse method that is available in the node interface that will return a so-called traverser. And the traverser is super simple. It's a Java iterable, which means that it basically has a hasNext and a next method, and you can iterate through it using the for each loop. And we use the traverse method to get that traverser back, and then we're just going to start iterating across it to get our result set back. The magic is in how we parameterize this. So basically, what parameters do we pass into the traverse method? And if you recall, what we talked about before was that we want to go breadth first rather than depth first. So that's the first parameter. Then we pass in what types of relationships do we want to traverse. We want to go rel types, nodes, because we want to traverse the nodes relationships in the outgoing direction. Then we pass in 2 types of so-called evaluators. And the first evaluator is called the end of graph stop evaluator. And the stop evaluator basically instructs the graph database when to stop traversing. In this case, we say, as long as you can find relationships of the nodes type, just keep traversing. Traverse until the end of the graph. The second evaluator is called the returnable evaluator. And the returnable evaluator basically says that out of all the nodes that we're going to visit, what nodes should we include in the result set? In this case, we say all nodes except for the start node, because, again, we want Mr. Anderson's friends, not Mr. Anderson himself. After we've done this, we've passed in these parameters to the traverse method. We get the friends traverser back. And that's the only thing that has happened. We've only positioned the traversal framework in the graph. We haven't actually started doing any traversals. So that, however, happens once we start iterating through the friends traverser. In this case, we use the for each loop. So we say, for each friend of the node type in this friends traverser. And then we print out some information. And that's going to go next, next, next on the friends traverser, which will use the parameters that we passed into the traverse method to evaluate how to walk the graph. As you can see inside of the for loop, we have some interesting methods and variables that we can access from the friends traverser. For example, we have something called the current position, which will access, ironically enough, the current position of the traverser, where you can get the current depth. And we also get, of course, the current node that we're visiting back. And so we can use that to print out the actual name of that node. So if we zoom in on this a little bit, the way we're going to do this is that we're immediately positioned on the first node, Mr. Anderson, because that's where we invoke the traverse method. What the traversal framework will do once we execute next on the friends traverser is that the first thing it's going to do, it's going to look at the stop evaluator. And it's going to, look at the returnable evaluator. And it's going to say, hey, okay, this node that I'm positioned on, should I return that? Should this be included in the result set? And in this example, it's going to say, actually, you are at the start node right now. The returnable evaluator is all but the start node. So let's not return that. Okay, interesting. Cool. So then let's see. Should I keep traversing? It's going to ask the stop evaluator. The stop evaluator says, oh, yeah, just keep traversing. Go until the end of the graph. And so then the next step for the traversal framework is that it's going to grab one of the relationships that matches this filter that we have at the end of the traverse method, which is type nose and direction outgoing. As you can see, from node 1, there are two relationships that match that filter. We're going to grab one of them arbitrarily. Let's say it's the first one that goes to node 7. We're going to traverse along that. We're going to end up on node 7. We're then going to ask the returnable evaluator, okay, what about this node? Should I return it? In this case, it's going to say, yeah, this is not the start node, so let's return that out. And that is our first result set. After that, we're going to hit next, and we're going to actually go breadth first. We're going to go back to 1. We're going to go down the nose relationship, the only other relationship that matched our pattern, and we're going to go down to 2. And at that point, we're going to return the Trinity node as well. And then we're going to keep traversing that way until we get to node number 13. At that point, the stop evaluator would say, yes, keep traversing, but there will be no more relationship that matches the filter nose in the outgoing direction. So the result set in this case will be as follows. We're going to print out Morpheus, Trinity, Cipher, and then Agent Smith. So that's all fine and dandy, but what if we wanted to do a slightly more complex query? So let's say that we want to model something in our domain like love. So let's say that we want to express that Trinity loves Thomas Anderson. So we create a relationship of the loves type between Trinity and Thomas Anderson, outgoing from Trinity. And then let's say that we wanted to have sort of a similar traversal to what we had last time, which is all the friends of Thomas Anderson, but don't return all the friends, just visit all the friends. But return only the ones that are in love. The code for that is actually very similar to the previous example. We're going to start with the traverse method. We're going to pass in breadth first and end of graph, the same as the last time. We're going to traverse the same relationships, nose in the outgoing direction, but the returnable evaluator. In the last example, it said all but start node, return all my friends. But in this case, we really only want to return the friends that are in love. And here you can see that these evaluators are actually just interfaces. And you can pass in your own implementations of these interfaces. In this case, you have quite a lot of syntactic overhead here in Java as a language. With closures in Java, this is going to be a lot easier to express. And in Ruby and Scala and Clojure, more functional style languages, this is super simple code. But setting aside sort of the syntactic overhead here, we really just pass in one line. And that's a line that starts with position.currentNode.has relationship. And it basically returns true if we have a relationship of the type loves in the outgoing direction. If that is true, then we're going to return the node that we're currently visiting as part of the result set. If not, not. Pretty straightforward, and basically the same code for printing out the result set, just some new text. So again, we're going to start at the first node, number 1. We're going to traverse along the nose relationship types. So when we get to number 7, we're going to invoke, again, the returnable evaluator. Last time around, that returnable evaluator was all but start node, which matched on node number 7. But now, as you can look at the code in the returnable evaluator, from the perspective of node number 7, it's going to return false. Because as you can see, there are no relationships of the loves type in the outgoing direction from node number 7. So it's going to keep traversing until it hits node number 2. And in that case, it's going to be true for Trinity, and we're going to return that. This example did not check if Trinity was in love with Thomas Anderson. It just checked all the friends in my friend circle that are in love. If you wanted to do that, then basically in the returnable evaluator, you would also verify that the end node of the loves relationship was the specific node you were looking for. Very simple. We're going to print out Trinity in this example. Okay, so that's the core representation API. This is the equivalent of talking about insert or select, etc. in SQL. The question then is, how do you implement your domain model? What if you have, for example, a person interface in your POJO, your plain old Java object, your person domain object, and you have name. In Java, you would usually represent that as an interface with, get name and set name. And how would you implement that using a graph database? Well, it turns out that it's very straightforward. Let's assume that you have that one person interface with get name and set name. Then the class that you use to implement this, let's call it person impl, using a graph database, will look something like this. It will implement that person interface, and the core variable, the core attribute of this class is called underlying node. And it's actually the only attribute of this. Traditionally, if you wanted to store a person in a relational database using something like JPA or Hibernate in Java or whatever OR mapping layer, active record in Ruby, etc., then what you would have is you would have an attribute here called name, a private string name. But with a graph database, you actually the only attribute you have is a reference to the underlying graph. So you store all state in that underlying graph. You get this reference passed into the constructor at construction time, and then the getName method, which would look like return this.name if this was in using Hibernate. Instead, it actually delegates to the underlying node, and it gets the property called name out of that. It casts it to a string and passes it out of the person implementation. And set name works the same way, except it's going to use the set property method. This is an interesting pattern because one of the consequences of this is that all the state that you have in your domain layer, all your attributes that would typically be declared inside of this person input class, like private string name, private int age, private string social security number, private whatever, all those things, are now actually delegated to the graph. So all the state is in the underlying graph database, which has interesting consequences. For example, the graph database is completely transactional. So all of a sudden, you can start working transactionally with your domain layer. You can start a transaction. You can start writing data using domain-level operations like set name, get name, set age, etc., to your domain layer. And then if mid-air you decide that, hey, this doesn't work, then you can just roll back. And it's going to be completely rolled back. And if another transaction, actually another thread, is concurrently working with the same domain object, the same actual person impl object, it's going to be able to read to that from that object at the same time as you're writing to it, because the database implements core transactional features and core transactional integrity. So in no way in your domain, nowhere in your domain layer will you be able to use, or will you have to use, things like synchronization, etc., which is a very powerful feature called software transactional memory, and is one of the approaches that we as an industry are using or inventing to handle the multi-concurrency challenges that we face now with these new parallel systems. So after a while, though, this becomes a little bit tedious because, as you can see here, there's some repetition of code. There's some repetitive code. Underlying node get property, underlying node set property. We're going to have to do that for every attribute. So there are a bunch of domain layer frameworks that intends to automate this. One is called Ki4j or Chi4j, which is a framework for doing domain-driven design in pure Java 5. Another one is called Jo4neo, which is an annotation-driven framework for basically annotating plain old Java objects, and they're going to be serialized into the graph. And the one that we're investing a lot of time and effort in is called Spring Data Graph, which is a collaboration we have with SpringSource, the backers of Spring Framework, which is very similar to Jo4neo, but even more powerful. Where you declare your plain old Java objects with annotations. And then Aspect J, which is an aspect-oriented framework, will introspect those domain objects and serialize them to the graph transparently. So if we look at the equivalent class as we did before, the person class, if you use that in Spring Data Graph, it would look very, very simple. You would declare your person class, you would declare a private string name, and then a traditional get name and set name method. But since you've annotated this class with @NodeEntity, which is equivalent to @entity in JPA or Hibernate, for those of you who are familiar with the Java world. Since we annotated this person with @NodeEntity, Spring Data Graph will know that this domain object actually belongs to the graph. So it's going to look inside of this domain object. It's going to see that there's a private string name in here. Okay, cool. Whenever you write to this actual variable, it's not going to be stored in the variable. It's actually going to be delegated to the same construction that we saw before with an underlying node, but it's going to be done completely transparently. So it alleviates you as an end-user programmer from having to write all this code with underlying node, etc. It also allows a number of really powerful features, such as you can see in here, you can declare some of the attributes as indexed, and then you can do lookups based on, for example, the name in this case. There's a bunch more things we can talk about Spring Data Graph, and we actually have an upcoming webinar about that you can sign up on our website later, I think this month or next month. Okay, so that's some of the core features about graph databases. But what about some use cases? So we've talked about social data today. We used the matrix example. That's actually not a fictional example. One of the largest social networks in the world are using us to map relationships between people, social relationships. And it looks very similar to basically the social network example that I just used with from the Matrix movie. But the interesting aspect here is that if you look at the structure of the social network, the graph database, of course, doesn't really care what properties you store on the nodes or what types the relationships are. So if you look at the exact same graph, but we remove the properties and we start adding other types of properties, all of a sudden we have a completely new domain. In this case, the example that I chose was spatial data, which is a very popular way to use graph databases. A huge telecom company is using Neo4j for doing exactly what I'm talking about in this example, where you use nodes to represent points or points of interest. So, for example, a hotel, a restaurant, and whatnot. You have relationships that represent the roads between these. And then you can say simply, how do I get from Omni Hotel to some other place, right? And then it's basic graph algorithms to find the shortest path between the point where you are right now and the point where you want to go. Lends itself very well to graphs. But our spatial support actually goes one step further. It actually supports core true spatial operations. If you annotate your nodes with properties like latitude and longitude, as you can see in this example, you can do core spatial operation like say, I'm now at position XYZ, well, I guess position XY, and give me all the points of interest within 30 miles from where I am right now. And that core spatial operation is supported as well in Neo4j. Okay, so we talked about social and we talked about spatial. But what if you combine both of them? If you look at the left-hand side of this slide, you can see that it's the spatial data that we talked about before. And on the right-hand side, you can see it's a network, a social network. And in this case, we have recommendations added to this social network. So we have node number 3, whose name is Emil, and we have node number 42, whose name is Peter, and they're friends. But we also have a recommendation that Emil likes this restaurant called The Tavern. And we've actually attached a weight to that. So Emil really seems to like this restaurant called The Tavern. And that's, the recommendations is what ties together the spatial graph from the social graph, or the geo graph from the social graph. And this all of a sudden allows for some really powerful queries. For example, let's say that you wanted to find out, give me all hotels or restaurants within 30 miles from where I am right now, but rank them according to the recommendations by my friends. and by my friends of friends. And by the way, when you rank them, I want you to weight my my friends higher than my friends of friends, because I trust my friends implicitly more. If they like a place, then it's more probable that I like it as well. So that query is a 2 or 3 liner in Neo4j, and it's actually a very complex query. This is all enabled by the fact that the graph model is so flexible at expressing all domains, or most domains at least. And you can easily take one domain, like social data, and another domain, spatial data, and layer them on top of one another, which allows for some really new type of interesting queries to be answered in real time, super fast. Another example is financial data, fraud detection. This is what very large financial systems or financial services firms, they want to know, assuming a number of transactions, like Emil withdrew cash from this ATM. Emil paid money to this restaurant, etc. A number of these kinds of transactions, figure out how money ended up, from one place to a suspect. In this case, node number 1 is the Godfather, Mr. Godfather. Node number 13 is an ATM, and we want to find out how did cash actually go, from the ATM over to the bad guy. In this case, node number 1, the Godfather, and that's the shortest path algorithm. And if you have thousands of transactions per second, if not more, and you have a huge graph of people and cash infusion places as well as suspects, then doing these kind of queries in real time really demands graph database or something similar. So that's another example of a very graph-oriented system in the financial sector. There's a bunch more in telecom, in finances, in really anything web, but we don't have a lot of time. We're actually running a bit short of time. We need to be done in 6 minutes, so we're going to move on. So we talked about the programming model. We've talked about some examples. What about some system characteristics? Well, one of the first and most important things is that Neo4j is completely disk-based. Our number 1 commitment in terms of technical values is robustness. We pride ourselves on never ever losing data, which is maybe odd that you would have to mention that for a database, but actually many of these new NoSQL systems choose for good reasons, but choose availability over durability. So there are a bunch of instances where they can lose data. For our customers, big enterprise style customers with mission critical systems, losing data is not an option. So once you commit, data is on disk. It's completely transactional. We talked about this already. It scales up. It can handle many billions of nodes, and it's been in 24/7 production for a long time, over 8 years now, with demanding customers, military customers, and others. So we talked a little bit about performance. Let me drill down into one example on that. And the caveat on this is that this is a micro benchmark, and it's a contrived micro benchmark. And like in everywhere in computer science, if you actually want to know about the performance, you need to model your actual application and then run your examples or your benchmarks yourself. Having said that, though, this benchmark was actually generated by one of the biggest social networks in the world, who contacted us a while back and said, hey, we love your model, but we want to know actual performance. And so please show me some benchmarks. We went back and forth a couple of times. We, being the honest geeks that we are, we said that, hey, we can prove anything with benchmarks. So give us a scenario that is relevant to you. And the scenario that they gave us was as follows. Assume that you have 1,000 persons. Every person has an average 50 friends. Grab 2 people at random and see if they're connected at max depth 4. We implemented that using 2 backends, one relational and one was Neo4j. And we eliminated disk I/O from this because we wanted the overhead of the actual model, not of going to and from disk. So if we look at the numbers for this, the query again was grab 2 people at random, for example, Mike and Kevin, and check if they're connected. Not even how, but if they're connected. and Mike in this case are connected, for example, through Emil, Marcus, John, and Kevin, right? So running that query in a relational database, a popular open source relational database, if with 1,000 people, you have an average of 2,000 millisecond query time. We ran this in Neo4j, and with 1,000 people, we have 2 millisecond query time. So that is substantially faster. But we weren't happy enough with that, so we actually upped the ante a little bit, and we added 1 million persons to the social network, and still average 50 friends. So 25 million total connections in that, running on a small laptop with a 300 megabyte heap. We grabbed 2 people at random, and we checked if they're connected. And that question on average is still 2 milliseconds. It's a pretty optimized type of query for a graph database. So what are some pros and cons compared to a relational database? There's no OR impedance mismatch. We talked about this, whiteboard friendly. There's some OG, if you will, object graph impedance mismatch, but that's very, very low compared to the relational model. It's easy to evolve schemas because it doesn't enforce any schemas. We can represent semi-structured info with 3 properties on one node and 1 property on a second node and 10,000 properties on a third node. We can easily represent graphs or network structures with performance. The drawback is that it lacks in tool and framework support, and this is the universal drawback of NoSQL systems. Relational databases have been around for 30 years. There's few other implementations, although many new ones are appearing every day, more graph databases. We were very alone 3-4 years ago, but now there's a bunch of other graph database implementations, which is a good thing. And there's no support for ad hoc queries. But actually this third one is less true now that we released Neo4j 1.4 about a month ago, because actually that includes a new query language called Cypher. And this new query language uses a very simple SQL-inspired pattern matching syntax, where you use 3 core components of a query. You say, start from this node, or these nodes, match this pattern, and then return these. And the start clause here is very simple. It just says, give me the user whose name is John. Start from that node. And then the match class draws a little graph, if you see, uses sort of ASCII art here. It says, a node called user connected with a friend of relationship to another node, and then connected with a friend of relationship to a third node. Return that third node. It's a very simple query. You can do more powerful stuff. You can iterate through starting points, and you can filter. So you only return nodes that have, for example, in this case, an age property that is greater than 18, and you can return specific properties. In this case, the name of that node. But I don't have time to go into more details than that. There's a third or a second query language, really a groovy DSL for traversals called Gremlin, which is also incredibly popular. And it's based on the Tinkerpop stack. And it uses basically Groovy to create a very powerful DSL for traversing graphs. You can Google Gremlin and graph, and you're going to find lots of information about that. As I mentioned before, there's a bunch of language bindings, Python, Ruby, Scala, Erlang, etc., for pretty much any language you want to connect to a graph database from. And this has been a fast-paced 1 hour, but we haven't even mentioned half of it. There's clustering mode where you can use master-slave replication to cluster across many databases. There's a web admin interface and a lot more things. Go to neo4j.org and download it, and you can check it out. And you can also read through. There's lots of documentation out there on all of these features. So in conclusion, graphs are awesome and Neo4j is awesome. Neo4j is available to download today from neo4j.org/download. There's 3 editions. There's Neo4j Community, which is fully featured, includes everything you've seen today, and as we mentioned, a lot more than that. And it's completely free under the GPL. And then there's 2 more editions, one called Neo4j Advanced and Neo4j Enterprise. And these are licensed under the AGPL, which basically means that if you're open source, we're open source. So if you're developing an open source project, or for example, if you're in research, you can use these for free as well. But if you are writing closed source software, proprietary software, then you need to buy a commercial license. And the advanced and the enterprise editions include features like monitoring management, high availability clustering, as well as actual 24/7 commercial enterprise class support. So I want to end this by encouraging you all to go to neo4j.org to download Neo4j and check it out. I also want to encourage you to look at Spring Data Graph, which is available from the URL you see here in the middle. We have a forum which is available on lists.neo4j.org or neo4j.org/forums. It's both web-based and mail-based, and we're pretty vigilant about answering questions. So if you have any questions that we don't have time to answer today, just jump onto the mailing list and ask them there, and we'll be sure to jump in. You can also reach out to us on Twitter. Just attach the hashtag Neo4j, and we will get back to you. And that was the 1 hour. I will stick around here for a couple more minutes and answer questions. Other than that, I thank you all for listening in.
Okay, Emil, thank you very much for a fantastic webinar. We have a lot of questions, far more questions than we have time to get to today. So let me tell everyone that has asked a question, we are going to download all the questions and actually put together a question and answer sheet, and we'll post that. We'll probably post that up on our forums as soon as we can collate all the answers to the question. So if you've asked a question, we will put an answer to it up on the neo4j.org community website. But I don't want to disappoint you by not having any questions answered, so I'm going to pick one, and I'm going to ask Emil, what's the capacity? How many nodes can Neo4j handle?
That's a great question. So the current upper level for storing nodes and relationships and properties is 32 billion nodes, 32 billion relationships, and then 64 billion total properties. So that's a total of 128 billion primitives, and that is for one machine.
Excellent. Okay, thank you, Emil. So we're going to post the answers to all the questions that have been asked. If you have a burning desire to get your question answered faster, please feel free to go to the neo4j.org community site and put your question into the forum, or put your question up on Twitter, as Emil has described. So I want to thank everyone for giving us an hour of your time. We understand that your time is valuable, and we appreciate the fact that you've stuck with us for an hour today. I hope you've learned about graph databases so that you can address some of the questions that you have. We have a short survey that immediately follows the webinar. So if you've learned anything today, or if you might have learned something today, please take 30 seconds to fill out the survey. It's only 5 questions long, and we do read all of the comments in the survey as we try to make the webinars more informative for you. For those of you who didn't arrive at the very beginning, I already know right here what the most commonly asked question is, and that's, have we made a recording of this webinar? And the answer is yes, that we have. And as soon as we post the recording up onto our servers, we'll send a link out to the recording to everyone who showed up today. So expect to see the link in your email tomorrow. So thank you very much for attending the webinar today, and I want to thank Emil for delivering a fantastic webinar. Thank you very much. Bye-bye.
Thanks, Adam, and bye-bye.